In this video, I am going to discuss another problem from Lioville's theorem. First, I will write down the problem. Suppose you have an entire function and also it is not a constant, right? Suppose that fz is an entire function and also it is not a constant. It is not a constant function. Okay, because constant functions are also entire functions. So in this case, I'm considering an entire function which is not a constant, right? Then the problem is, now I have a function which is an entire function. The problem is prove that fc, the image of this function fc, is dense in C. This is what I need to prove, right? I have to show that image of this function is dense in C. Okay, right. Let's begin the proof, right? So what is the meaning of dense? Dense means, so first I will write down, I need to prove that fc is dense in C. In other words, I have to prove that image of this function is dense in complex plane. What does that mean? It means that so what does that mean? The meaning is, if fc is dense in C, I need to prove that the closure of fc is going to be equal to C. This is the closure of fc, or in other words, closure of the image under this function, right? Okay, what is the definition of the closure? The definition of the closure means, suppose I have some point w in my closure, right? So suppose w is in the closure of fc, right? That means for any neighborhood of this w, so I'm choosing any epsilon ball which is centered at w, right? So for any epsilon greater than 0, I can find some point, right? So for any epsilon greater than 0, I can find some z naught in C, right? Z naught in C, such that if z naught is in BW epsilon, right? So this is the idea of the closure, right? If I draw a small diagram, this is what it says. So I have some point W, right? If W is in the closure of FC, it does not matter what is the disk that you are going to select. So if you select any disk of radius epsilon, you will be able to find some point z0 in C such that its image is inside this disk. Right? So if z0 is inside this disk, this is the idea, right? Okay. Now I have to show that the closure of FC is going to be equal to C. Okay, right. So I'm using the method of contradiction. So first I will assume that the closure of FC is not going to be equal to C, right? So to the contrary, I will assume that FC closure is not equal to C, right? Okay. What does that mean? The closure of FC is not going to equal to C, right? That means there exists some point W naught in C and it does not contain the closure of FC or closure of the image, right? Which does not contained in FC closure, right? Or in other words, W naught is in C and it would belong to the complement of the closure of FC. Okay, this is the idea, right? It is in the complex plane, but it does not belong to the closure of the image of function f, right? That means it does not contain it is contained in the complement of its image. Okay, right. So if something is not in the closure, right, now W naught is not in the closure of FC, that means I can find some epsilon naught or delta, right? So I will select epsilon naught. So I can find some epsilon naught positive such that if Z minus W naught is greater than epsilon naught for every Z in C. Okay, so I'll draw a small diagram to elaborate this idea. So this is my complex plane and I have a point that does not belong to the closure, so it is W naught. So because it does not belong to the closure, I would be able to find some neighborhood epsilon naught, right? So this is my disk whose radius is epsilon naught, right? So it does not matter what is the Z value that I am going to choose. My FZ values are going to lie outside this disk, right? So I take, it does not matter what Z value that I'm going to take, right? I chose some Z value and I evaluate the function value at that point. Then I'm going to lie outside this disk, right? If I am going to lie inside this disk, that means W naught belongs to the closure, right? So yeah, Is the idea, right? Now I'm going to use this fact to apply the Lioville's theorem. Now I'm going to construct another new function, capital G, right? So now I'm going to define another function. Let capital G is at is equal to 1 divided by f is at minus w naught, right? Okay, now I know that the magnitude of f is at minus w naught, it is greater than epsilon naught, right? So this part will never go to 0, right? So what can I say from that? G z is an entire function. Okay, right. Now what can you say about the modulus of Gz? It is going to be equal to 1 divided by f is at minus w naught, right? And f is at minus w naught is greater than epsilon naught, so 1 divided by f is at minus w naught is going to be less than 1 divided by epsilon naught. Okay, now this proves that Gz is bounded, right? So Gz is a bounded function, bounded, and also it is entire, so it is bounded entire function. Okay, right. So now I can apply the Lioville's theorem. So Lioville's theorem states that if we have an entire function which is bounded, then it should be a constant function, right? So by the Lioville's theorem, Gz is going to be a constant function. I will call that constant function as k, right? Gz is equal to k, right? So k is equal to 1 divided by f is at minus w naught. So f is at minus w naught is 1 over k, and this would give us f is at is w naught plus 1 over k. Right. So we got a result which says that f is a constant. So f is a constant. But in the problem it says that f is non-constant function. F is a non-constant function. So this leads to a contradiction. Okay. So hence this is a contradiction. Therefore I can say that therefore the image is dense in C. In other words, the closure of Fc is going to be equal to whole complex plane, right? So image of F is dense in the complex plane, right? Okay, so this is a good application of Lioville's theorem and the definition of closure, right? So I used those two facts when I was solving this problem. I hope you understood what I did. If you have any questions, you can mention your questions in the comment section. Thank you for watching.